Hello to a problem session. Today we have a very standard problem, and sometimes students kind of get tripped up by this problem because there's a similar problem in previous chapters students have done, and that problem previously you have a same kind of incline, but a block, and this slides, and you can find this acceleration. So this problem is all about just the center of mass motion. There's no rotation, tumbling of this block. Okay, so this is this problem is actually inside this problem also, but on top of that there is a rolling, so this problem needs to be done differently. Let's see. So at some time t, just like over here, some time t, we look at this forces and get. So at this here also, sometime t, we examine the forces. But in addition, we have to examine the torques. So this is the center of mass, and say at this time, acceleration is E, acceleration A down like this. And if I look at the forces, I will have a gravity force straight down, that would be mg. And then down here, there is a momentarily, when it's rolling, there's a point of contact, and that point of contact has a rolling friction Fr. And then there is a normal force which kind of almost goes through this center of mass, but we'll just take it as it goes through center of mass. This is a normal force that way. As a result of these three forces, center of mass is moving with an acceleration A. So you have one principle is summation of all the forces equals to mass and acceleration of the center of mass. So this there's a equation like that, and then another equation is about rolling, and when it's rolling, let's call it acceleration alpha. For the rotation part will be tau about cm axis through cm, and we can see what the axis looks like over here. That's the axis. So this is the axis that passes through cm, and that's equal to the I about that axis. And alpha. And we need to make sure that the sign, beware of the sign. Okay, so we put together, and from this we can find A, acceleration A, and once you find acceleration A, then just like over here, once you find acceleration A, and it's constant, and if you have to go distance d, and v is 0 here, and time is t here, and time t equals 0, then you can show that d equals to half a t square, and so t will be equals to 2d over a square root. So that will be the answer. Okay, so from there we just feed like that. So the main task for us is to use how to make use of these things to find the acceleration over here. And let's do that out now. Okay, that's the strategy. So this is our strategy, and do it out. Okay. So to do problem for a CM motion, F equal to M A CM, we just look at a free body diagram. So this is, we use free body diagram as before, and so this is the theta. Mg is this way, capital Mg is that way, normal is that way, F rolling friction is that way, and acceleration is that way. So of course we only need a equation along the, so this is the x-axis, so this Mg component on that direction, this angle theta, so this is angle theta. So this gives me, along this axis, gives Mg sine theta minus Fr equals Ma. So this is one equation we get. So if you find like how I got this and more help on this, you have to go back to the previous chapters and practice more solving free body diagram problems. Okay, we are right now in a rotation chapter, so I'm going to focus on this rotation part. So to get the rotation part, we have to look at the torque about the center of mass. So over here, axis is this way. So any force that going through the axis, like mg and normal, they will have a zero torque. Tau is 0, tau is 0. So the only force we will worry about is this Fr. And from here you can see that's the lever arm for this force. So if this is the alpha, say this is a positive orientation, then the torque is also a positive orientation. So that's what I was talking about, the sign. And about this axis, the I about this axis is half mr square for cylinder. So you have a cylinder like that. The radius is r and the axis is that way. Then the formula for moment of inertia about this axis will be that. So we have now all the information. So Fr times this lever arm times r equals I times alpha. Now alpha, this alpha and this A will be related, because you can see the distance traveled will be how much the distance along the arc, the surface of the arc will be related to arc length, and that will be the angle. So the angle and the distance are related. So delta theta is related with r times delta theta is along this direction is a delta x. Then divide by delta t, it happens in time delta t. So divide by delta t, and so r omega is related with v along that direction. And so if I take a d dt of that, r d omega dt equals dv dt. V is in some x component, so this is x component. So r times alpha is actually A. So that's the relationship between them. And so we can write down, I'm not interested in alpha, so I can write down I over R A, and so you can simplify as FR is just equal to I over R square A, and because I is half MR square, so this is half MA. So you use this and this, we are able to find mg sine theta minus half MA equals MA. That just means A equals to M just got cancelled out from this. Interesting, the mass of the cylinder doesn't matter. And this over here becomes 3/2, then this 2g over 3 sine theta. So this is important from our previous thing, strategy. We saw that between here to here, if the distance is d, and time here is 0, time here is t, and the acceleration is a, and v over here is 0, then this is a one-dimensional problem, and t is equal to 2 d distance d over a square root. So that's putting a in there. So I'm going to get square root of 2 will cancel out. You have a 3d over g sine theta. So if theta was 0, this would be infinite time. That's, of course, if theta was 0, is incline is like this. So it's never going to get there. When theta is at 90 degrees, if you drop straight from here, if theta is 90 degrees, it's going to, but it's dropping, but not dropping, is rolling. It's rolling along. Then it's going to be 3d over g. So this is the answer. Okay, so that does it for this problem. This is an important problem because you can see we made use of this separation. So this is a motion of CM of center of mass, translation motion of center of mass, and this is rotation about an axis through the CM. This will be the theme for a lot of problems that have to do with rolling. Hope this helps. Take care. Bye.